Hello, everyone. I am Mitsunori Uemura of Ritsumeikan University. Let's start the 7th week of the Advanced Topics in Robot Control. This week, I would like to introduce some more advanced robot control described here. Force control has been proposed as a control method that takes into account the case where the robot is in contact with an object. When the robot performs a task, the robot comes into contact with an object. In such a case, we may want to control the force applied by the robot to the object as desired. To see the basic principle of force control, let's use the simplest example, as shown in this figure. In this example, the tip of the single-joint robot is in contact with an object. Let F be the force with which the tip of the robot pushes the object. The purpose of force control is to make the force applied by the robot to the object a desired force. Therefore, the control objective is to make the actual force F converge to the desired force Fd. When the robot is at rest, the force F can be derived from the statics, as shown in this equation, where tau is the torque exerted by the actuator attached to the joint and Lf is the distance from the joint to the contact point. In force control, we use a feed-forward torque tau Ff such that the robot pushes the object with the desired force Fd. From the previous statics, the feed-forward torque tau Ff that produces the desired force Fd is shown in this equation. In fact, substituting this tau Ff into the tau in the previous statics gives F equals Fd and the control objective is realized. However, this is only true if the robot is at rest. Therefore, if the robot has multiple joints, this statics is not valid because the robot is moving and controlling the force at the same time. Even if the robot is at rest, the desired joint torque cannot be achieved by the feed-forward torque alone due to modeling errors such as static friction of the robot joint. Therefore, the actual torque input is designed with the feedback of the force error as in this equation. This force F is measured by a force sensor attached to the tip of the robot. Note that the force data itself cannot be used directly for feedback. The reason is that force has the same dimension as torque, so the instant the controller fed back the force, it instantly affects the actual force, and further feedback of that force instantly changes the force even more. This instant force feedback loop causes strong oscillation of the force. Therefore, we should use the integrated force error in time, as shown in this equation. This allows the actual force F to converge to the desired force Fd after enough time has passed. In most cases where force control is actually used in a robot, we control the force while controlling the robot motion. In such a case, we should use both this force controller and some motion controllers. Instead of controlling the force directly, impedance control indirectly controls the force by enforcing the mechanical behavior of the robot. In impedance control, the mechanical behavior of the robot and the contact force are controlled by simulating the situation where elastic and viscous elements are attached to the tip of the robot, as shown in this figure. The control objective of impedance control is to make the actual force F converge to the desired 1 Fd. The same as in force control. In the same way as before, let's use the simplest example to understand the principle of impedance control. The statics of this single-joint robot can be expressed in this equation. To simulate the forces of the spring and damper attached to the tip, the actuator torque is designed in this way, where K is the stiffness of the virtual spring, XD is the equilibrium point of the virtual spring, X is the tip position, and D is the viscosity of the virtual damper. Let's set the stiffness K of the virtual spring to satisfy this equation. Then, when the robot is at rest, x dot equals 0, so tau equals minus LFFD, and the control objective, F equal Fd, is realized just as in the case of force control. The difference from force control is that the mechanical behavior of the robot can be set as desired by setting up the virtual spring or damper with the desired stiffness and viscosity. You can see how the mechanical behavior of the robot is controlled by the impedance control in a video introduced in the description box. Output zeroing control is a method that can control systems where the number of inputs is less than the system's degrees of freedom. Such a system is called an underactuated system. Compared to systems with the same number of inputs and degrees of freedom, such as normal industrial robots, underactuated systems are more difficult to control stably. In cases such as humanoid robots, where a large amount of torque around the ankle causes the foot to leave the ground, we should control the underactuated system. Let's take the example of the two-joint robot as shown in the figure. Assume that the first joint near the ground of this robot has no actuator attached to it and the second joint has an actuator attached to it. The motion equation of such a robot can be expressed in this way, where M11, M12, M21, and M22 are each element of the inertia matrix of the robot. H1 and H2 are each element of the centrifugal Coriolis term, and G1 and G2 are each element of the gravity term, and tau2 is the torque of the actuator attached to the second joint. The difference from a normal two-joint robot is that there is no actuator attached to the first joint, so the first line on the right side is 0. Therefore, the first row of this equation is unactuated dynamics. Conversely, the second row is driven by an actuator and is therefore the same as the dynamics of a normal robot. Such an unactuated dynamics is called zero dynamics. Since the second row is the same as the dynamics of a normal robot, a control method like the computed torque method can be applied to realize trajectory tracking with respect to a joint angle. If we design the trajectory of the controlled joint angle well, we can stabilize the zero dynamics. Then both the controlled dynamics and zero dynamics are stabilized and the entire control system becomes stable. This kind of control method is mainly applied to gait and humanoid robots or to brachiation robots. In this video, a humanoid robot without actuators in its ankles maintains its balance to prevent it from falling over. In this case, the actuators in the knee and hip joints can directly control the angle of the knee and hip joints, but not the angle of the ankle. Nevertheless, by designing the desired angle of the knee and hip joints appropriately, the stability of the ankle joint motion, which is not directly controlled, is guaranteed, thus allowing the robot to maintain its overall balance. Model predictive control is one of the most actively studied methods in the field of control theory in recent years. Model predictive control is a kind of optimal control, and is a method of calculating the optimal input in real time. Model predictive control can take into account constraints such as input limitations and can be applied to nonlinear systems, making it applicable to many real-world control systems and achieving high control performance. However, model predictive control has the disadvantage that it requires a detailed model of the controlled system in order to calculate the optimal input. Therefore, if the model of the controlled system is not known in advance, the stability of the control system cannot be guaranteed and we cannot expect sufficient performance. In addition, calculating the optimal input in real time requires a huge amount of numerical calculations. Therefore, even with recent computers, it is difficult to calculate the optimal input for complex systems in real time, or even if it is possible, it takes up a lot of computational resources of high-performance computers. In the video introduced in the description box, model predictive control is applied to a humanoid robot in a simulation. As a result, the humanoid robot skillfully balances itself and generates a very complex behavior. Model predictive control is applied to many other applications, such as self-driving cars, so let's check out the videos and documents. Control methods based on AI, which has made dramatic progress in recent years, is also being actively researched. By using AI-based learning, complex tasks such as obstacle avoidance and walking can be accomplished without the need for elaborate controlled design. In the video introduced in the description box, a humanoid robot walks and runs while skillfully maintaining its balance while overcoming an obstacle using AI. This research, conducted by the group leading Google's AI, has received a lot of attention. However, as you can see in the video, the control results are not sufficient to be implemented in a real robot at this time. Also, because of the huge amount of training required, it is not practical to learn the behavior in a real environment at this time. Another major problem is that we cannot theoretically guarantee the stability of AI. Therefore, it is not suitable for tasks where stability is crucial. The method of controlling a robot using visual information acquired from a camera is known as visual feedback control or visual servo. Since humans carry out a variety of tasks by using visual information, the development of visual feedback control is important for robots to perform a variety of tasks like humans do. While vision sensors provide more information than other sensors used for robot control, they also have some disadvantages, such as being two-dimensional information, low frame rates for many cameras, high computational costs for image processing, and frequent occlusions. The video presented in the description box uses a sensor that solves one of the weaknesses of visual sensors, low frame rate, so that the robot can follow objects at high speed. A control method in which multiple robots work together to accomplish a task is expected to grow in the future. If multiple robots can work cooperatively, the number of tasks they can accomplish will increase, which will expand the applications of robots. The video introduced in the description box demonstrates a control method in which multiple robots cooperate to hold and move an object. Control of bipedal walking robots is one of the most common robot control, along with control of robotic manipulators. The traditional control method bases on the zero-moment point and plans the trajectory of the mass center of the robot. This method has long been the standard for bipedal walking control. However, this method is based on trajectory planning, and it has been difficult to adapt to unexpected disturbances and ground irregularities. In recent years, methods based on dynamic trajectory planning and dynamic feedback control have become mainstream. And even if there is unexpected disturbance or ground irregularities, the robot can walk without falling down by generating appropriate movements in real time. A good example of this is the walking robot from Boston Dynamics. Boston Dynamics walking robot can adjust its gait to continue walking even if it is disturbed during a walk. It also achieves acrobatic movement thanks to its superior hardware and trajectory planning. Here is a video of it in the description box. Another biped walking that is attracting a lot of attention is passive walking, in which a legged machine with no actuators or sensors at all can walk stably down a slope. Passive gait generates a stable walking motion despite the fact that it does not use any control at all. Therefore, it is assumed that there is a stabilizing principle of the legged machine itself, and a lot of researches have been done to reveal this principle. Moreover, since passive walking is an extremely energy-efficient gait, it is thought that it can provide crucial insights to energy-efficient walking control. In the description box, I introduce a movie of a passive walking robot that can walk about 4,000 steps. Finally, I would like to introduce homework for this week. For this week's homework, summarize and report on 2 or more of the advanced robot control introduced this week or of interest that you search on your own. In that summary, clearly state the control laws using equations so that someone reading the summary can implement the control method. Each control should be summarized in about 1 page. Please submit the created report through Manabar. That concludes this week's class. Thank you for your hard work.